We're going to try and find out the structure of this compound here. We've got C6H9O2N. It's got nitrogen in there. Okay, then they give us the infrared spectrum and the proton NMR spectrum on the left there. So let's first of all have a look at the infrared on the right here. Of course, all of this stuff here is the fingerprint region, so we can't say any one of those particularly any one of those peaks is associated with a particular bond. That's too difficult to interpret. This peak here, this about 3000, is not very useful because it's, if you look at your infrared chart, you'll see that's due to CH bonds, which are present in more or less everything. More useful, I think, though, we have got a carbonyl. Definitely, that is very characteristic of a carbonyl. And then I was thinking about the nitrogen. Okay, so we've got a nitrogen here. Now, if you've got an amine at all, a primary or a secondary amine, you're going to have hydrogens attached to that nitrogen, and that gives you quite a big peak over here, round about where you get the carboxylic acid OH peaks around there, and there's nothing there. So I don't think there's definitely not a primary or a secondary amine. I suppose there could be a tertiary amine because there's no hydrogens attached to that, but I don't think that's the case. Sorry, tertiary amine would be if you had 3 carbons attached there, but I don't think that is the case. And then your eye is drawn to this peak here, and 2200. If you look that up in your infrared chart, you'll see that that is characteristic of a nitrile, or cyanide, C triple bond N. So I'm pretty sure that's where the nitrogen in this molecule is. It is attached. It's part of the nitrile group, not as an amine. Okay, so there's quite a bit of useful information from the infrared spectrum there. So we know, just to summarize, we have got sorry about that. To summarize, we know we've got a carbonyl. We know we've got a nitrile. There's no amine, and also there's no carboxylic acid or alcohol group. And that, again, if there were those, we get big peaks over there, and we haven't got that. Okay, so that's quite useful. I'm going to get rid of all of that now. Give myself a bit of space. Right. Okay, let's have a look at the proton NMR we've got here. There's our ppm scale there. Now, good check here is you're supposed to have 9 hydrogens, and we check the integrated traces given in red. So we've got 3 plus 3 plus 1 plus 2. Yeah, that makes 9. So that's all consistent with that. One thing which strikes me from the proton NMR, which we already deduced from the infrared, is that there's no alcohol groups and there's no amine groups. And we can tell that because those sort of protons don't split. They give us singlets. And we haven't got any singlets at all in the spectrum. They're all like quartets or triplets, doublets. Yep. So there's none of them there. And also confirming from the infrared, there's no carboxylic acid because, again, well, we'd get a singlet, and also it'd have that OH, that hydrogen has a ppm of about 12, and there's nothing anywhere near as high as that. So we've ruled all that out. Let's try and see what this spectrum could be then. Okay, so right now, the thing that first caught my attention, this spectrum, I think, is this doublet here worth 3. Okay, so that means we've got a CH3, and the carbon to which is attached, because it's a doublet, that carbon can only have 1 hydrogen attached. So here, at these positions here and here, you can't have a hydrogen there. Now, one of them could be another carbon. We've got 6 carbons to think about, so let's put a carbon down for one of those. We have something attached to that. Okay, and let's put, we know we've got a cyanide group in there, so a nitrile group, so let's put that there. Now that would mean that the carbon, this one here, the carbon next door to it, that one, has only got one hydrogen attached, so that would give us a doublet. So that, I think, is that there. Now, this hydrogen here, now this is the singlet. This is the one with the integrated value of 1 here. It's got to be, because that's the only one. Now, would that be a quartet, how we got it set up? Well, it would be, because if we look at the carbon, if you look at this carbon here now, the carbon it's attached to, that one there, is attached to 3 hydrogens. So that would give you a quartet, as long as, and this is important, this carbon can't have any hydrogens attached to it, because if it did, then that would mean that, this hydrogen would not be a quartet, it'd be more than a quartet. Okay, so this one has got no, how can we have that? Well, we know we have got a carbonyl group to play with. We know we've definitely got a carbonyl in this compound. So if I put the carbonyl there, then that's the splitting pattern of this one and this one. Oh, absolutely right. Okay, a doublet and a quartet. Now we've got 4 of our carbons there. We've only got to worry about 2 other carbons. There's 6 carbons in this molecule. What strikes me next is, I'm going to do this in yellow, is, can you see we have got a triplet with an integrated value of 3 and a quartet with an integrated value of 2. That is very characteristic of an ethyl group. Okay, if you just think about that, so this is, these protons here, that'd be 3 of them, integrated value 3, and on the carbon next door you've got 2 hydrogens, so that's going to be a quartet, a triplet, whereas these 2 hydrogens here, well, on the carbon next door you have 3, so that's going to be a quartet. Another thing which strikes me about this is the ppm is pretty high. It's just over 4, and that is usually when there is an oxygen attached to this carbon. So I think we've got that there. Right, and then if I just transfer this group here, stick it onto the rest of the molecule, then we have accounted for everything. We have got there, we've got C6H9, we've got 2 oxygens, and we have got a nitrogen. We've got 2 oxygens in an ester linkage there. That is completely consistent with the NMR spectrum. So I think that is the structure that we're looking at in this question.